last lesson we looked at direct stress and strain, and this is what most people tend to think of when they refer to stress and strain, but there is also a thing called shear stress and shear strain. And what we're going to look at in this video is what they are, how they're different to direct stress and strain, and then how we can do some calculations around them and why they're important in an engineering environment. And the aim of the lesson today is for you to be able to perform shear stress and strain calculations and also to cover calculations for the modulus of rigidity. So let's get started on it. So hopefully you can remember from the previous lesson that direct stress or compression is a straight pull on a bar or a bolt or something like that, a straight pull. Now shear stress is different in that it's actually offset. So I've got an example here where we've got that's direct stress there, and down below here we've got shear stress where there is a difference between the axis of the forces. They're not lined up, and that causes a block, for example, with a push on the top and the bottom to actually distort slightly like that, and that is shear stress. I've got some examples of shear stress in real life. So first of all, a good example of where shear stress is used is to calculate the force required to punch through, for example, a sheet of steel. So you've got a punch here coming down on a piece of steel over a die to punch a round hole in it, like for example in a washer. And you would use shear stress and strain to do the calculations to work out how much force you might require to actually achieve that. And in this particular situation, the two shear stresses, the bit we're interested in are these bits here where the shear stresses are actually applied. Now another example of shear stress is one like this one here, where we've got two forces, one acting on the bottom plate pulling to the right and one acting to the top plate pulling to the left, and the only thing that stops them sliding apart is the cross-sectional area of the bolt here. This is the thing that actually stops it from pulling apart, and that is called single shear because we've only got one surface area resisting the shear. That's single shear. You can also get double shear, which is a situation where you have a fork rather than a straightforward plate, and this time we've got 2 times the cross-sectional area of the pin actually resisting the force that's actually being applied. So that's called double shear. Now shear failures can look like this. And this is a typical shear failure. If you've got a beam that's heavily loaded very close to the support, it won't bend very much, but it can fail under shear, and you get a typical failure line of about 45 degrees. If too much load is added to a beam, that's where it will actually fail. Okay, so here we have an example of shear stress in action. Now you can see on this simulated steel shaft, I've drawn a rectangle there with nice 90-degree corners. If I twist it like this, you'll see that becomes a parallelogram because the shaft, when it's twisted, actually produces a shear stress on the surface of the shaft. If I go the other way, you can see it as well, like that, quite clearly producing the parallelogram that you associate with shear. So normally, if you overstress a shaft like this, it will snap and fail in shear, and I'll give you an example of that. Great expense here. I've got a sesame seed breadstick, and I can just twist this end to end. I'm not bending it. If I just twist it like this, it will actually fail in shear like that. And that's what will happen with your drive shaft if you overdo it pulling away from the traffic lights. It could potentially fail in shear just like that. So, as we move on, we've got a few more Greek letters to look at. Now from the formula sheet you'll find that shear stress is this funny curly T equals force over area, and shear strain is what looks at first glance like a Y equals A over B. Now the shear stress symbol is actually called tau, and that's a Greek letter T really. Tau equals the force over the area. We'll look at that in a moment. And then shear strain is actually gamma. That Y looking symbol is actually a gamma, which is a Greek G. So just so you can remember those, tau for shear stress and gamma for shear strain. So shear stress is defined as the load per unit area. And that's the actual formula there, as we saw a moment ago, is the force over the area. Now the important thing to remember is that the unit for stress is the Pascal, or newtons per metre squared. We'll use Pascal because that's what the exam board are using. And the area, critically, is the area resisting the stress. Now in this particular example here, the example we've got here, we've got the two plates of metal, one being pulled one way, the other one being pulled the other way, and the thing that stops them sliding apart is the single cross-sectional area of this pin. So here's a question. Let's have a look. Let's work through this. So what is the shear stress on a pin 15 millimeters in diameter when subjected to a load of 500 newtons? First thing to do is to calculate the cross-sectional area of the pin. So area, as we know, is pi r squared, and in this case pi, the radius, we've got to convert from 15 millimeters into meters. So 15 millimeters is 7.5 millimeters. Divide that by 1,000 to convert to meters is 0.0075 squared to calculate the area, and that comes out to 0.177 times 10 to the power of minus 4 meters squared. Now the shear stress we know is the force over the area. So in this case the force is 500 newtons divided by an area of 0.177 times 10 to the power of minus 4 gives you 2.83 times 10 to the power of 6 pascals, or 2.83 megapascals. So here's a question for you to have a go at. Read it through very carefully and now pause the video. Okay, the answer you should have got is 155 megapascals. If that's what you got, well done. If you jump on to the next section, if you're not sure, we'll go through it. Okay, so here we have question 1. A 22mm square steel pin is used to hold two strips together when they're subjected to a force of 75 kilonewtons. Now the pin here is 22mm, so let's draw this in here. And that's 22 and that's 22 there. So therefore, first thing you need to work out is the area in square meters. So therefore, 22 millimeters equals 0.022 meters. Because remember, you just jump the decimal place along 3 times to convert from millimeters to meters to divide by 1,000. Therefore, the area equals 0.022 squared, which comes to 4.84 times 10 to the power of minus 4 meters squared. And then the shear stress is simply the force over the area, in this case the area resisting the pull, so therefore shear stress, which is tau, as you may remember, equals the force, which in this case is 75 times 10 to the power of 3, because it's kilo, divided by the area, 4.84 times 10 to the power of minus 4, and that comes out to 155 megapascals, or mega newtons per metre squared. And that's all we need to do. nice and clear, showing all the steps, and that should be fairly straightforward. Okay, so we've considered shear stress. So what about shear strain? Now, shear strain is defined as the amount the material moves when it's under a shear stress. I've got a little diagram here which shows that quite clearly. This is your shear force here. You've got these two arrows offset because that's what shear is. You get a tiny bit of movement here, and the length you're interested in is normally, in this case, the thickness of the piece of material. But as with direct strain, the numbers you were talking about are usually very small. It's very hard to see shear strain on a piece of metal, for example. You do need accurate measuring equipment to measure it. You can't see it with the naked eye. And shear strain, gamma, is defined as the movement divided by the length. And as before, the unit for strain, because it's actually two lengths, one length divided by another, the strain is actually a ratio. It doesn't actually have a calculated unit. So let's move on to do a calculation based on that. So here we have, what is the shear strain on a block 8 millimeters thick when the measured movement is 0.025 millimeters. So we've got our shear strain equation here, A over B, and we simply put in A, which is the actual movement, which we're told is 0.025 millimeters, divided by the thickness itself, which is 8 millimeters. Because both units are in millimeters, we don't need to convert them through to meters because the units cancel out, and the shear strain on this comes out at 0.003125. So, as you would expect, here's a question for you to have a go at based on shear strain. And here it is. So read through the question, and then when you're ready, have a go at it. So pause the video now. Okay, so the answer you should have got is 0.009 millimeters. If you got that and you're comfortable with how you did it, well done. Jump on to the next section. Otherwise, I can go through it for you. Okay, so question 2. Calculate the maximum allowable movement on a steel block 4.5 millimeters thick if the shear strain is not to exceed 0.002. So let's write out the equations first of all. Okay, so what do we know in this? We're told the shear strain is not to exceed 0.002, so we know that. The movement is the thing we've been asked to calculate, so I'll put a little question mark over that. And the thickness, or the distance, is 4.5 millimeters, so we know that as well. So we've got to rearrange the equation to get A on its own. And to do that, we need to multiply both sides by B. That way it cancels out on this side and leaves us B times gamma equals A. So I'll write that out, A equals B times gamma. So B is the thickness. Now, because we're dealing with strain, it's not necessary to convert to meters. So we can leave it at 4.5 millimeters. So 4.5 times the strain, 0.002, and that comes out to 0.009 millimeters. Obviously, if you divided by 1,000 and converted that to meters, your answer would be meters, and you need to state meters there. But that's a perfectly good way of doing it. So, final part of the lesson. This is looking at the modulus of rigidity. Now, this is calculated by dividing the shear stress by the shear strain. And to put the actual letters in, the letter for modulus of rigidity is G, So G equals tau shear stress divided by gamma, which is shear strain. Now, I'm not going to go through a calculation on this because you know how to calculate shear stress and shear strain now. It's very similar to direct stress and strain. So we'll go straight on to the question in a moment. Just to remind you though, that when you're designing a shaft for a gearbox or something like that, a material with a high modulus of rigidity will resist twisting better, which is normally desirable in, for example, a gearbox or an engine. So here's a question for you to have a go at, which combines all the ideas we've done this particular lesson. And so a coupling shown, and there's the coupling there, as a steel pin holding the two components together in double shear. So in other words, what we're saying here is that the force, or the pull, is being resisted by 2 times the cross-sectional area. You've got to bear that in mind in your calculation. You're given the force and the diameter of the pin, and you're told the shear strain is 0.0025. So you don't need to calculate that, you've been given that, and you've got to calculate the modulus of rigidity for the coupling. So if you're comfortable with that, pause the video now. Okay, the answer you should have got for that is a modulus of rigidity of 63.7 gigapascals, or 63.7 times 10 to the power of 9 pascals. If you got that, well done. Go on to the end of the lesson. If not, we'll go through it. Okay, so here we have practice question 3. Let's read through it. The coupling shown has a steel pin holding the two components together in double shear. Now what double shear means is that we've got the force pulling this way and this way. It's resisted by 2 cross-sectional areas on the same pin. So we need to bear that in mind in our calculation. The force is 25 kilonewtons and the diameter of the pin is 10 millimeters. So that's 10 millimeters across there. Let's put a diameter, just mark that in there. 10 millimeters there, and the measured shear strain is 0.025. So we're given the shear strain, we don't need to calculate that, and you've got to calculate the modulus of rigidity for the pin in the coupling. So first of all, let's work out the cross-sectional area of the pin on its own. So this cross-sectional area, CSA, equals pi r squared, which in this case is pi times the radius. The diameter is 10, so the radius is 5 millimeters. Divide that by 1,000, gives us 0.005 squared, and that comes to 7.85 times 10 to the power minus 5 meters squared, because we've converted it to meters. Now, because it's double shear, the area resisting the force is going to be twice the area of the pin. So let's write that out. So this comes to 15.7 times 10 to the power minus 5 meters squared. So that's the area resisting the force. Now the shear stress we know is tau is force over area. So let's write that out. In this case it's 25 kilonewtons times 10 to the power of 3 divided by the area resisting the force, which we know is 15.7 times 10 to the power minus 5, and that comes to 159 times 10 to the power of 6 pascals. Or you could say 159 megapascals, like that. Now we're told the shear strain excuse me, is 0.0025. We've got to calculate the modulus of rigidity. We know the formula for that. We can get that from the formula sheet. So I'll write this out anyway. So we can put the numbers in. 159 10 to the power of 6 divided by 0.0025 gives us a final answer of 63.7 times 10 to the power of 9 pascals, or 63.7 gigapascals. So there we go, quite straightforward if you break it down into little chunks and write it out very clearly to explain what you're doing. Okay, so we've pretty much got to the end of the lesson now. Well done for sticking with it. And by now you've probably realised that actually direct stress and strain and shear stress and strain are very similar. And it's true they are. The calculations are carried out in much the same way. Stress for both of them is basically the force divided by the area resisting the stress, and strain is the change in length or the movement divided by the original length. Very, very similar, and the way you calculate the modulus of rigidity is very similar to how you calculate the modulus of elasticity for stress and strain. So direct stress and strain. So really, they're very, very similar. And if you've got the hang of one of them, it shouldn't be too difficult to get success on the other one as well. So as usual, there's some practice sheets for you to go to. They start off with fairly straightforward questions and get more difficult as they go on up towards distinction standard. So have a go at those. The answers are on the sheet, so you can sort of self-correct, and if you can see if you've gone wrong, if you've got the wrong answer, you can go back and check your working. See you on the next lesson.